Hey guys, here's a recording for you for the rest of chapter one, which is about representing motion. And this should get you through homework assignment number two. So the things we're going to cover today are motion diagrams, what the basic conventions are that the book uses, and they're pretty generally used in all physics. Vectors versus scalars. You probably recognize that term vectors, and scalars may not, but yeah, that's a very important one. We'll get to that pretty soon. So because we use vectors versus scalars a lot, and today it pops up. Then we'll get into distance versus displacement, and these basically are just straight definitions. And this gets to what I was telling you the other day when I gave you the study guide. Um, Words have specific meaning in physics, which is sometimes drifted a little bit when those terms pass over into common usage. And distance versus displacement is one of those. And speed versus velocity, which is the last thing we're going to look at, is also a huge, huge example of these. In your English class, speed versus velocity mean the same thing. They're just straight synonyms, but there is a subtle but important difference between these two, and it's very important that you know the difference between speed and velocity. And along the way, we will be introduced to a couple equations. Um, right, and like I say, this will get you through the first homework assignment. Now, I do ask you to watch this thing all the way through, even though if you look at the homework, it probably is going to make some sense because there are certain conventions and techniques that we use all through physics that I introduce here. I'm also going to show you how I want you to use the GFEW format for doing a calculation. So let's get into it here. First, motion diagrams. Motion diagrams. You can think of a motion diagram as a multi-exposure frame, if you will, where the dude's rolling along on his skateboard, and we take a flash, take a flash, take a flash, take a flash. So we have four positions as he rolls along. Now, when you create these on your own, you do not have to make them photorealistic. You don't have to be an artist. What you should use is just a dot. This is what's called the particle method. Your book refers to this. You're just representing the thing, whatever it is, as an infinitely small point that contains all of its mass. And generally, we put it at the thing's center of gravity or center of mass as it rolls along. And it's totally okay to just kind of put these next to our reference line here as well. Now, what do we mean by the reference line? Um, you always start the initial position as zero because the assumption here is that there's the same time interval from one to the next. So if this is 1 second that it took for him to get from position zero to position one, then this is also 1 second to get to position two and one more second to get position three. Now, it doesn't have to be seconds. It can be minutes or 10 seconds or half seconds or whatever. But whatever time interval you choose, you have to stick to it and be consistent. Now, why do we use zero for the initial position? Because that's what the stopwatch says when we first hit the go button. It says 000. That's the initial time. This is 1 second, 2 seconds, 3 seconds, and so forth. Okay, so that's a motion diagram. Now they're not always as simple as this. This is clearly a guy that's just rolling along at constant speed because he goes the same distance in each amount of time. But you can have more interesting ones, like this girl is going faster and faster. She's speeding up as she goes to the right, and you can tell that because the particles get farther and farther apart as the time intervals pass. And it's always the same time interval. So clearly she's going faster as she goes along here. And finally, the car is slowing down because it was going fast and it went some distance and then less distance and less distance and may have stopped right here. It's going to stop very soon. But this is an object which is slowing down. Now, this is also a reason why we really do have to put the numbers in, because couldn't this car also be going in reverse? Maybe it started at this position and was going backwards faster and faster and faster, right? And you really couldn't tell just from the diagram itself. Now, the fact that she's leaning forward is a tip off for the runner, but for a car, and certainly if all you're doing is looking at dots, yeah, you have to show what the first position was and then subsequent positions. Now, if the thing slows down and stops and then goes back the other way, then you're going to have like position four, position five, position six, and so on. So the numbers may be kind of mixed up and the dots kind of mixed up, but you can sort it out and piece it together what's happened. That's going, oh, fast, slower, slow, stopped, and then faster going back the other direction. So these are actually very versatile, very useful things. They're simple, but they help us visualize motion. That's why they call them a motion diagram. Okay, next we're going to go to the difference between distance versus displacement. But to really get it, we first have to talk about the difference between vectors and scalars. Okay, vectors versus scalars. As I said before, you've probably heard this term vector. Now you get to find out what it really means. Scalars you may not have heard of, but they go together like, hand and glove and heads and tails and so forth, vectors and scalars. Okay, in physics, we hang numbers on things. We measure them. Because numbers are easy to calculate. So yeah, we tend to hang numbers on anything that we can. Now, anything that we can measure, anything we can hang a number on, is going to fall into one of these two categories. Now, if direction matters, and this will make more sense when we look at some examples, but if direction matters, then it is a vector quantity. Okay? And if direction does not matter or it's meaningless, then it is a scalar quantity. Okay? So, for example, if I ask you, hey, how much do you weigh? And I would say like 200 pounds, right? Now, mass, 200 pounds, is that a vector quantity or a scalar quantity? And the way you check is to say, well, does it have meaning to say 200 pounds to the left or 200 pounds north? And no, it doesn't. That's gibberish. So that means that direction does not matter when we're talking about the mass of something, which means that it is a scalar quantity. Okay? Now, how about force? How about force? Now, as you know, force is a push or a pull. And the direction that you're pushing or pulling does matter. So, for example, if I say, okay, we have like the saloon doors that just hang, and they can swing freely. We have a saloon door there, and I have two students pushing on it with equal force. Does the door open or not? And the answer is, it depends. If both students are on one side pushing it the same direction, then yeah, it's going to swing open and they're going to fall down into the room on the other side. But if you have one student on each side pushing against each other in opposite directions, then it's not going anywhere because the direction of the force matters. So force is a vector quantity. Okay. Now, how about temperature? It's 70 degrees in the room, 72 degrees in the classroom as you're doing this right now. Is that a vector quantity or a scalar quantity? Does direction matter or not? Does it have any meaning to say it is 70 degrees north? And clearly it's not. So temperature is a scalar quantity. Now, as we go along here, we're going to talk about distance and displacement. And one of these is the vector and the other one is the scalar for distance and displacement and velocity versus speed. Anything that we can measure, any number we can hang on anything is either going to be a vector quantity or a scalar quantity. And there's things we can do with vectors that we can't do with scalars. So it is important that we know the difference. Okay, so that brings us to distance versus displacement. Short version, distance is a scalar quantity and displacement is the vector quantity. Sometimes all we care is how far something went. Other times we care about not only how far it went, but what direction it went. So for example, if you're running around a track, the track around the football field, running a quarter mile for your cross-country coach, the distance that you run is a quarter of a mile because that's how many steps you took. That's the distance over the ground that you took because we don't care about direction. Now, as we'll see as we move along, the displacement running around the track exactly one time is going to be zero. Zero displacement because we start and end in exactly the same position, and all that running and sweating didn't get us anywhere. So our displacement would be zero. Okay, let's show this to you. I think I can do this on the clipboard here. So let's see if we can get that popped up. I'm going to move this over to the side a little bit. Okay, wake up clipboard. There we go. Good deal. And we're going to focus. And we're going to blow it up so we can see it. All right, so we have, let's see, I'm going to move me down a little bit more. There we go, so we can see everything we're doing. Very nice. Okay, so we have a scale here to keep track of our motion. And first off, distance, all we care is how far we went. So distance, that is the scalar quantity, is how far. Okay, so if we start at this position and end at this position, well, how far did we go? Well, the way we figured out is we just count. It's very simple. We started here, so we went 1, 2, 3. And that's how far we went, 3. If we started here and we ended all the way over here, well, we count 1, 2, 3, 4, 5. And we went 5. Great. Now, what if we went the other direction. If we're talking about distance, we don't care about the direction. So again, we just count and we go 1, 2, 3, 4, 5, and the distance is 5, whether we went in that direction or in that direction. Doesn't matter. Okay, now what if we are doing like a round trip? So we start at the position -1 there, and then we go out to 3 and turn around and come back. And we come back and we finish at position -3 here. Okay, well, how far do we go? What is the distance that we travel in this trip? And again, we just count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The distance we traveled was 10. Okay, that's distance. Now, what about displacement? Displacement, that is the vector quantity. And for this one, we do care about the direction that we went. So if we started here and ended here, I think that's the same example that we did before. We went 1, 2, 3 again, but we went in the positive direction. So this is an important thing when we're dealing with vectors, or displacement in this case, when we're dealing with vectors, is we have to define what the positive direction is and the negative direction is. And the positive direction is forward and the negative direction is backwards. That's the way to think about it. So if we start here and end here, we went 1, 2, 3 in the positive direction. So our displacement would be 3 meters. But if we did it the other direction and we started here and ended here, it's still 1, 2, 3. That's the distance, but it's in the negative direction. So our displacement is going to be -3 meters. Okay? Now, what if we do that round trip thing again? Let's see, I think I started here. We turned around at this point. So we went to here and we came back. All we care about with displacement, and remember this, okay? All we care about with displacement is the starting and the ending position for whatever time interval we're interested in. And for this one, we're interested in the whole trip. So we started here and we ended here. So we went 1, 2 in the negative direction. And it doesn't matter what we did on the way. It doesn't matter what course or path we took. All we care about is where we started and where we ended. And in this case, it is -2 meters. That is our displacement for this trip. The distance was 10, but the displacement is -2. Okay? Now, we have an equation for this. There's no equation really for distance because, like I say, you can do it just by counting. But for displacement equation, the equation is this. It is delta x is equal to xf minus xi. And this is much less complicated than it may look at first. Okay, so first off, what is this triangle thing? It's a Greek letter delta. And it's shorthand for change in. So x, I should have mentioned this before, x is position. So whatever number we pull off our position chart here, that's the numbers we plug in here. So delta x means a change in position, but we just say x. So change in x, and that is equal to the final position. So x is x, but the little lowercase f there, and this is a small one down the end. It's a little I forget the word. Anyway, it's a little letter down to the side, so we can specify specifically what we're talking about. In this case, we're talking about the final position. So this is not two variables. It's not x times f. It's just specifying which position this is, and it is the final position. Okay, and this one is the x initial, which means the initial position, the starting position. So the equation is, for the change in x, delta x is equal to final position minus the initial position.